So we'll wrap up this section by talking about paradoxes, which I'm going to get at the idea that logic in some sense has its limitations. So we'll start by considering the following scenario. Suppose you have a student who has an exam tomorrow at 9 a.m. It's currently 9 p.m. and he thinks to himself, well, there's still plenty of time, right? There's 12 hours between now and then, and he decides he's going to start studying halfway between now and the exam. So halfway between now and the exam would be 3 a.m. 3 a.m. comes along, his alarm goes off, and he thinks, well, he's still sleepy, and there's still plenty of time. So again, he says to himself, he will begin studying halfway between now and the exam. Halfway between now and the exam. Okay, so halfway between 3 a.m. and 9 a.m., it's 6 a.m. He wakes up, he realizes he's still got to get ready for school. Luckily, he now realizes that he can continue this process indefinitely. He can continue to put off studying indefinitely using the same argument, right? There's still going to be some finite amount of time between now and the exam. He can just take that finite amount of time, split it in half, and when he reaches that halfway point, he's going to do the exact same thing. If he does this, he'll never actually reach the exam. This is what he thinks to himself. Now, does that seem like a logical, valid argument to you? It should definitely raise some red flags, right? Because you know that it is going to eventually hit 9 o'clock. You're going to be there. You're going to be given that exam whether or not he has found the time to study. But is it not correct that for any finite amount of time, even a very, very small unit of time, you can always cut it in half? This is basically what this argument is saying. It's saying there's always still going to be some finite amount of time left. You can always cut that finite amount of time in half. This is one example of a paradox known as Zeno's paradox, which roughly states that it's impossible to complete infinitely many things in a finite time. It's impossible to complete infinitely many things in a finite amount of time. And, right, it's applying here because he's got a finite amount of time between now and then, but he's doing this sort of infinite process of cutting this time period in half. There's a lot of different formulations of Zeno's paradox, some that you might have heard before, including the arrow. Another example that you might have heard of is called Achilles and the tortoise. The idea is that Achilles and a tortoise are running a foot race, and because Achilles is so much faster than the tortoise, he gets a head start. So let's say at the start of the race, here is Achilles at the start, and here is the tortoise who has gotten some kind of a head start. Maybe way down here is the finish of the race. So the idea is that in order for Achilles to win the race, he's got to beat the tortoise, but in order to do that, he's got to pass this distance between himself and the tortoise, right? The first thing he needs to do to pass the tortoise is to reach the point where the tortoise started. Well, it's going to take him some amount of time to get from the starting position to wherever the tortoise started, and during that time period, the tortoise has made some progress. Not as much as Achilles because he's slower, but he's certainly made some progress. So now maybe the tortoise is up to here. Okay. Well, the next thing that Achilles has to do is he has to reach the place where the tortoise is at this next time interval. So he needs to now pass this distance between where the tortoise started and where the tortoise was at this time. But while he's done that, the tortoise has once again moved forward. Not as much, but some amount. Right now, here's the tortoise. And again, in order to pass the tortoise, Achilles now has to move this distance. Every time Achilles reaches the point where the tortoise was, the tortoise is still moving, so they've made some progress ahead. And using this argument, we conclude that Achilles can never pass the tortoise, because every time he reaches the point where the tortoise was, the tortoise has moved ahead, even if it's a very, very small distance. Therefore, Achilles will never catch the tortoise. Now, this doesn't seem right. We've seen a fast person and a slow person race. The slow person gets a head start, and we can see that the fast person is able to pass the slower person eventually. So this leads to a paradox, and it's kind of hard to define what a paradox is, but it's something that seems self-contradictory. We saw an example of this on the very first day when we looked at the statement that this statement is false. This is something that we sometimes call the liar paradox. But how do we formalize the idea of a self-contradictory thing in logic? Well, unfortunately, there's not really one very careful or consistent definition of what a paradox is in logic or math. We can use that term to mean a number of different things. So instead of getting into kind of the nitty-gritty of what it is, there's a lot of different possible definitions. Instead, we're just going to look at a few examples. Oops, sorry. So the first example I'm going to look at is something called the paradox of material implication. This might look familiar to one of the informal fallacies that we saw before. So the idea with the paradox of material implication is the fact that because a statement of the form P implies Q, oops, oh boy, try that again. So, since a statement of the form P implies Q is only false in that single case when P, the hypothesis, is true, but Q, the conclusion, is false, this can lead to some conditional statements which are technically true, but in some sense problematic. So for example, let's look at the statement that says, if Donald Trump, apologize for the polarizing example here, if Donald Trump never had children, there would be world peace. Certainly doesn't seem true. But technically this is true, at least using our formal logic that we have developed, because the hypothesis is false, right? Donald Trump never had children. That's a false statement. Donald Trump had 5 or more children. So this is a false hypothesis, and anytime the hypothesis is false, we say the entire statement is vacuously true. So this is a paradox in the sense that it seems contradictory. It seems false even though it's technically true. It certainly feels uncomfortable, right? Similarly, any conditional statement that has a true conclusion is going to automatically be true. So you could say something like, if Boston is the capital city of France, then Providence is the capital city of Rhode Island. It feels contradictory because the premise is certainly false and it has nothing to do with the conclusion, but anytime the conclusion of a conditional statement is true, the entire conditional statement will be trivially true as well. So this is what we call the paradox of material implication. Let's look at a couple more. We have Russell's paradox. This is a classical mathematical paradox that has to do with the origins of set theory. And set theory is what we build all of mathematics on. So we're going to discuss sets a little bit more formally later in the course, but the idea is that when you're trying to develop some particular collection of axioms by which you can model the arithmetic of numbers, the mathematician Bertrand Russell came across a problem with how we define a set or a class, but right, we think of these objects as sets now. Most axiomatic systems would assert that for some well-defined property, there is a set made up of exactly those objects that have that property, right? We can talk about the set of natural numbers as the set of, maybe not natural numbers. We can think of the set of even numbers as the set of integers that are divisible by 2. Right? Usually when we're thinking about sets, we're saying as long as you have some well-defined property, there is a set made up of objects that have that property. But Bertrand Russell, discovered that the set defined by the set of all sets X that are not a member of themselves. So the set of all sets X such that X is not an element of this itself, the set X. This is a problem, right? Because if R is a member of itself, right? R should be a set because it's got this well-defined property. But if R were a member of itself, right, is R an element of R? If R is an element of R, then that means that it satisfies this property, which means it's not an element of R. So that would imply that R is not an element of R. But on the other hand, if R is not an element of R, then by the definition of this set, that would imply that R is an element of R. So we've reached this sort of thing that's self-contradictory. The paradox was eventually later resolved using development of other axiomatic systems, but this was this was sort of a very big deal in the developments of mathematical set theory. So the last paradox that we'll talk about is something called the heap paradox. This question asks, how many grains of sand are required for a collection to be considered a heap, right? How many grains of sand do you need in order to have a heap of sand? I mean, heap's not really well defined, but maybe we could at least agree on a couple of things. First of all, that let's say if you have 10,000 grains of sand, that's going to constitute a heap of sand. Maybe less than that as well, but at least if you have 10,000, right, we're going to say that at least is a heap of sand. And probably we can also agree that if you remove a single grain of sand from a heap of sand, the resulting pile is still a heap. These two things seem reasonable. They seem like reasonable properties that a heap should have, and yet putting them together leads us to some uncomfortable conclusions, right? Because if 10,000 grains of sand is a heap of sand, and we can remove a grain and still have a heap, then that means 9,999 grains of sand is still a heap. Well, using the second property again, we can remove another piece, so now 9,998 grains of sand is still a heap, and we can continue this forever using just this second property, using sort of like a reverse inductive argument in a sense, but eventually that's going to lead us to the conclusion that having no sand at all is still a heap of sand. So having these two properties that seem like they are reasonable enough when put together leads us to something that seems like a paradox. So this is just a couple of examples of paradoxes that we see in mathematics. It's certainly not an exhaustive list. And again, we don't really have a very well established definition of what constitutes a paradox. And there's been many mathematicians and philosophers who have studied the ideas of paradox, and they've grouped it in sort of different ways. There's this sort of school of thought that says that there's veridical versus falsidical paradoxes, veridical being things that seem absurd but are actually true. Seem absurd but are actually true. Later in the course, when we talk about Hilbert's Hotel, that's an example of a veridical paradox, versus a falsidical paradox, which is something that seems false and in fact is false. Right, so for example, Zeno's paradox with Achilles and the turtle. Achilles is going to pass the turtle eventually, so that there's some actual, there's something actually wrong with that argument. Another mathematician has tried to sort of categorize paradoxes by grouping them into the logical versus the semantic. So in this case, we're using logical to mean having to do with the mathematical syntax of an argument. So a good example of a logical paradox would be Russell's paradox, right? The set of elements that are, or the set of sets that are elements of themselves, versus semantic, which has to do more with the meaning behind the symbols. So the liar's paradox is an example of a semantic paradox, right? But again, this is not something that mathematicians sort of have all agreed upon as being the correct ways to group paradoxes, and I'm leaving out a lot about paradoxes because it is such a wide-ranging topic.